You're the founder of OpenStar, and you're building fusion out of New Zealand.
I completed my PhD in superconductivity. The modern world is technology, and all of that technology actually made it the normal people's hands through the miracle of commerce. Government had just published this report. It basically said the language was going to go extinct. Te Tarangi never got major government funding. Nothing is actually impossible. Superconductors will levitate intrinsically. We're building fusion reactors, one of the fastest kind of fusion startup projects in the world. The dream is to make energy so cheap that you wouldn't even need to meter it.
This is Mark Pawlikowski, and welcome to the TechMates podcast, where my partner Henrik and I explore how Kiwi and Aussie founders are reshaping the future and what sets them apart. Henrik and I have been part of successful companies in Silicon Valley and Europe, and now bring that expertise to partner with entrepreneurs in Australasia. By sharing the personal stories of successful Kiwi and Aussie founders and how they got here, we hope to inspire you to dream big. This is TechMates, bringing an outsider's perspective to the stories of those daring to disrupt down under. Let's dive in.
Ratu, yeah, great to have you on TechMates. So you're the founder of OpenStar, and you're building fusion out of New Zealand, which is two very crazy things to be doing. How did you get into this? What's your background? Where are you from originally to kind of figure out how you got here?
That's a very broad question. How do you get into this particular situation? So by background, if I just take one step away from starting OpenStar, so I completed my PhD in superconductivity, particularly engineering. So thinking about large systems that use powerful superconducting magnets to do something better. My research focus was on hopefully making hybrid electric aircraft. So just like a Prius, burns fuel, but, has an electric drivetrain, has some batteries, helps buffer out the energy. You can make the same kind of arguments for aircraft, but in order to make that all work and actually be able to carry passengers, you need to move to superconductors, which are just much better at handling the electricity and in particular making really strong magnetic fields. And those magnetic fields are really what's like providing the torque in a motor generator, and so making really power dense motor generators for aircraft. I was looking at the kind of full systems package on that rather than kind of getting into either the material science too deeply or thinking about aircraft too deeply either. It was actually like, how do we get these superconducting magnets to work? Backstepping from that again, I did my undergraduate in physics and economics, so always interested in how kind of solving hard problems in the physical world could actually lead to strong commercial outcomes. I say strong commercial outcomes. What I really mean is changing people's lives in a really meaningful way. If you look at the world around us, I think the modern world is technology, and all of that technology actually made it the normal people's hands through the miracle of commerce and innovation. There are very few examples of a widget that everybody would interact with on a daily basis that was given to you by the government. It's usually free markets and free innovation, open innovation that gets this stuff into people's hands. But a lot of that progress was driven by kind of underlying physical insights about how the world works and how we can manipulate the world around us to unlock those advantages. So that's always what I wanted to do, like even way back before high school. I didn't quite know deeptech, and deeptech is suddenly in vogue. I think back in my undergraduate studies, everybody was starting apps, and then crypto was a huge phase, and the world of bits will always be very enticing for a lot of people. But for me, it was always, what are those kinds of real world physical insights that could really change the way people live? And that's probably what led me here.
And going back even more, I read somewhere that you were quite inspired by your grandma. Maybe you can tell us a little bit more about her background, because that's a super interesting story in itself.
So if I go all the way back, she's my grandma. So like any person growing up, she was just my grandma at first. It's kind of this funny thing. It's like you grow up, and as you become more mature and you understand more about life, you get to know the people in your family differently, right? Like, I think we've all had conversations with our parents now that we're adults. And it's like, oh, I get to speak to my parents like they're adults. Remember, my grandmother was just my grandma. And I was like, a child growing up, kind of learning about her as a person, but with this added layer of like learning about her through the eyes of other people. So my grandmother, Dame Katarina Ratu Mataira, got a knighthood for helping save Te Reo Māori as a language, save it from extinction.
Wow.
And by the time I was getting to know her, that kind of seminal work of her career had already been completed. People in Māoridom knew who I was as soon as they heard my surname. It was this really strange kind of royal family treatment. And like I said, growing up, you start to get an appreciation for why why that is. I think in terms of like OpenStar and how it ended up having the biggest effect on me, it was really this question of what can you do with the life that's given to you? Like, what's the biggest kind of challenge or set of responsibilities you could take on? What's the biggest impact? And this is the real privilege of my life, right? Like, we all benefit from having role models in life, because in some sense, for role models, they don't just tell us how to be, they also show you the breadth of what's possible. And it's like no understatement to say that Te Reo Māori was going to go extinct. By every measure that linguists use, it had effectively dropped down below the critical mass for everyday spoken languages.
Can you give us some backdrop? So Maori is kind of the native language of the native people of New Zealand, right? And then when the colonists came, I guess they spoke English because they were British colonists. And then over time, as New Zealand got settled, English was like the main official language. Is that kind of right?
It's a little bit more grim than that. So my mum is actually a good example. So, I mean, this whole story is about my grandmother, but my mother comes from a generation where Te Reo Māori speaking was being actively discouraged, not just by the state, but also in Māori families who were trying to promote assimilation for their kids, right? Like being a fluent speaker was not a source of prestige or acceptance or career opportunities. It wasn't the future. And so I think it was actually, quite late in the process of colonization where it was actually, okay, this is the new world order, right? You're going to have to go to university and get an accounting degree, when you grow up, and learning Te Reo is not going to help you do that. That shift is really what started to pull those numbers down. And so my mum was actually adopted out from my biological grandmother. But in her household, her parents spoke fluent Te Reo. She should have been able to learn it at home. She had teachers at school who spoke fluent Te Reo, but it was an active decision that was made in quote unquote the best interest of children to not learn this. And what that ended up creating was a situation where, oh wow, if we don't teach it to people, it's going to go extinct. And so it goes from that decision about how do you best raise kids for a modern world, let's call it, versus what is a language as a full treasure, as an entire cultural phenomena. What responsibility do we have collectively to keep it alive? And if you view it in that light, is it worth saving? Like, could you tolerate not just your kid not learning it, but like, could you bear the thought of no one speaking it, and 50 years pass and it goes extinct? And so I think those are quite kind of two different views of it. And in that context, what happened was my grandmother was basically at the stage of doing a master's degree. And her supervisor at the University of Waikato got this, government had just published this report. It basically said the language was going to go extinct. And her supervisor just looked at her and said, what are you going to do about it? And just like threw down the gauntlet for the challenge. I think so my grandmother was involved in two major movements, separated from each other in a very clever way. One was kura kaupapa, so flipping the educational model on its head for kids and saying, like, let's not do this suppress Māori thing, but let's just teach everything in Māori and just immerse these kids. So she was involved in that movement. And I think that's the one that people would have considered really obvious as like a shift away. But the other movement was actually a movement called Te Atarangi, which was entirely focused on adults, because a lot of this damage had already been done. So there's clearly a lot of people who had been raised and started going through life and realized they were missing this piece, realized that they would be willing to take up the responsibility of keeping this thing alive and take out that element of like a schooling system enforcing it on you and coming into it by choice, that like, this is something that I want to be a part of. This is something that I want to have as part of my life. And that movement was a huge part of pulling the number of native speakers up above that kind of critical mass. So, and this all happened before I was born. But for me, it comes down to this idea of like, just how hard are things? Like, all challenges are actually just people challenges because people do everything. Mm-hmm. They're all engineering challenges, all technical challenges.
That might change with AI, though, right?
Well, I mean, even AI is being built by people. We could get into that. That's a whole argument. But in that sense, that's about as hard as it gets. You're talking about major like demographic societal phenomena involving hundreds of thousands of people, and a phenomena that has enough momentum in it that it has led to a particular outcome every other time that linguists have seen it. stand up to that and say, no, we can do something about this.
Wait, Ratu,
Like, it doesn't have to go this way.
how did your grandmother save Maori from extinction?
By participating in the building of those two movements. So in particular, I think the obvious one is the kura kaupapa. That's just teaching kids an immersion, and like cajoling a schooling system to kind of accept this. In New Zealand, that led to a restructuring of how you could propose how a school worked. And so there's specific legislation that went through that allows kura kaupapa to exist and have the mandate to be the way they are. But te atarangi was probably the major insight that was quite different to how it had played out around the world, which is this realization that people will come to the responsibility of keeping the language alive on their own recognizance if you give them the opportunity, right? And if you bring together people with that purpose, you can achieve what you need to. So like te atarangi never got major government funding. It wasn't like going on banging on the doors of Parliament and asking for gazillions of dollars to solve a societal problem.
Mm-hmm. Mm-hmm.
It was talking to people who cared and building a movement in behind that, and then just getting on with the job. And it was enriching for the people who wanted to do that. But that hadn't happened anywhere else, or the other languages that had kind of gone past that point of no return.
That's so interesting. Do you think New Zealand is unique in its ability, whether it's the people or how small it is or how well the society functions and the high trust that you have generally, that it's the only place that's been able to like save a language from extinction?
I think we are very unique in this. And I think in the stories of colonization and how, let's say, Western societies have displaced indigenous cultures around the world, I think Māoridom, like even the nature of how te reo Māori started to retreat before this kind of revival movement, there's definitely a lot of classic colonial kind of state action involved, like telling kids they can't speak te reo in school and you're going to get caned if you do. So there is that element to it. But actually, a lot of it was just, this is the new way things are going to be, and English is going to be what's best for my kids. But the reason I labour that point is that colonization for Māori in New Zealand and our society and the history of it, I think Māori retained probably the highest level of agency and self-determination of almost any indigenous culture through a colonization process in the world. I'm not trying to say that to make it sound like it wasn't a painful process, but we were extremely lucky to be able to kind of hold on to, a bunch of that culture and a bunch of those treasures, and give them life again, as those trends started to shift back the other way, and you can kind of move towards a decolonization process, because there are plenty of indigenous cultures around the world that did not have that luxury. There are kind of cultural treasures in societies around the world that are lost because they didn't survive that filtering, and that's a tragedy, and we should count ourselves extremely lucky to have been able to hold on to those things and then give them a rebirth.
What were the cultural kind of undertones that first led Maori to be in decline, and then later, I'm sure society also had to participate, right? I'm sure your grandmother had to leverage kind of the broader consensus or just inspire people to see something different. What do you think that were those deeper kind of trends that people were, I guess, following that led them to first, reject Maori and then sort of get excited about sort of teaching it to kids again?
I think it really was that juxtaposition between the life decisions and who's making them for who and why. And so it's I'm going to prep my kid best for life. And so I'm a parent thinking about, or I'm a teacher running a school, and I could be reasonably callous and just say, the teachers were being, quote unquote evil. But we could just assume they had good motives. And it's like, well, how am I going to prepare these kids to, exist in a modern world? Going back then, English speakers are very much like this today as well, which is like language is a tool, and they just have a very utilitarian view on it.
Mm-hmm.
And so you have to be posed the question, does language have an intrinsic value beyond just being a tool of communication? The way my grandmother put it, to put it really succinctly, even on that point, was beyond the cultural value. There were ideas and concepts and emotions and feelings that she could not figure out how to express in English in anywhere near the same way as she could speak in te reo, and vice versa, to be honest. They have their different histories, they have their different contexts. And so I think if you're looking at it and here are your teachers and parents making life decisions for how you're going to grow up versus a collection of people who are interested in the societal value of a cultural treasure in its entirety, not just any particular person in it, the motivations are really different, and what people are willing to do changes really. And so again, like Te Tarangi was for adults. You know, they had already gone over, like, I turned 18, I went to uni, I got a job or whatever it was. And they said, actually, I feel a calling to go back and contribute to keeping this language alive and enriching my life in that way. And that particular shift in who's making what decision, I think I'm sure it actually plays out in lots of places, to be honest. But a lot of people who are set up for that, they're basically just rejecting the way that they were brought up as a mistake. And like generation on generation is always an opportunity to do that.
Right. And I assume you speak Maori? You speak Te Reo?
No, that's a terrible assumption.
Do you not?
No, I don't. And you've caught me in one of my deep kind of soulful regrets of my life so far. So I'll say something reasonably arrogant. I've been very busy doing all sorts of crazy stuff, like filling my head with, physics and economics and commerce and, trying to build companies and, build a business. And like, I have tried learning Te Reo Māori 3 times, in particular through Te Tarangi, once in undergrad and then twice during my PhD. And it's hard, right? Like the adoration and respect that I communicate for people who went and took that on is because it becomes a big part of your life when you do that. You have to actually have space for it. This is not just it's not of a point where you can just do it on Duolingo, let's say.
Is that your next company? Next?
No, I have plenty of cousins and I'm sure one of them will do that. But like so much of it is actually finding opportunities to be immersed in the language and the culture. And that takes time, it takes attention, and it takes commitment. And the reality is I tried it 3 times. And what I found was trying to pour my brain full of physics and, university at the same time as trying to kind of absorb that part of my heritage was too much for me, to be blunt.
But why didn't your grandmother speak to you when you were growing up?
This goes back to the Te Tarangi piece again. She viewed it as a choice, basically. Like, it's not something, I think also from the success of Te Tarangi, she wasn't particularly worried if you didn't pick it up as a kid, right? And that, if you had the chance and opportunity to go to a kura kaupapa and get completely immersed, in primary school and high school. In fact, those schools, the kids come out speaking English, Māori, and usually another couple of languages fluently. Like, they're very impressive for creating polyglots. But, you could argue I speak the language of mathematics or the language of physics.
Fair enough.
So kind of dopey way to say it.
Yeah.
And so you pointed out, like, what's my next company? Like, honestly, if OpenStar, reaches whatever conclusion it's going to, or my path in it reaches whatever conclusion it's coming to, I'd go hire a CEO to replace me, or whatever these things are. What would I do? I'd go and learn Māori. That would be the next step for me. Then round myself out as a human being.
Not just physics. That makes sense.
Not just physics. And, no one's complete as a person. You can get to, your 60s and still have things that you want to add in and round yourself out on. So you found a very particular part of me.
And so the key learning from your grandma was like, nothing is hard enough to tackle. And that's kind of what you took from her mostly.
Yeah, it's nothing is actually impossible. You can look at the kind of most important treasures or most kind of pressing crises that face your generation, and that success probably boils down to building belief in a movement committed to just taking action towards that thing. And so by the time fusion comes around for me, in my career, and in particular the kind of reactor we're building, this thing called the Levitated Dipole, it was really a question of, well, why not? What's your excuse for not taking this on? Is it too big? Is it too scary? Is it too much? Is it too impossible? And I had a really clear framework and foundation that none of that was true, right? Like, I had really no excuse but to tackle it and give it my best shot.
Yeah, and we'll get into that. But curious, when did you get interested in physics, and like, when did you decide, okay, this is going to be what I want to do for the next 20, 30 years?
That's a good question. I think more broadly, the first thought in my head was being a scientist. So falling in love with trying to figure out how things work, I was always a why kid. And I was also a pull everything apart to see how it was made kind of kid. I honestly, like all the way up to actually getting to university, it turns out I had this funny idea that scientists wore white coats, and therefore I signed up for a chemistry major because they wore white coats. It wasn't until I did chemistry at university that I actually realized I'm not cut out to be a chemist and I don't enjoy it very much. And it turns out it's this other thing, physics, that is like actually the thing. And that was certainly part of like what I enjoyed about science kind of leading up to that, really solidified that I'm not just a generic scientist. I was meant to be a physicist. And no more white lab coats for me, except for photo shoots, which is always quite funny. And, you can do a lot of work on a whiteboard instead. If you want to be theoretical, you could put together some cool gizmos if you want to do experiments. But to actually answer your question, I don't remember when it happened. Like, I've just always been that way. And I think I was a little bit of a late bloomer in terms of like opportunities to like really get my teeth sunk into it. I met people over the course of growing up and in my career now who just like got into physics or electronics or engineering at such a young age to like a really deep degree, right? It's the classic, building a robot in your bedroom when you're, 8. Like, I wish I had that childhood. That would have been sick. But I was actually a relatively late bloomer. Like, if you had looked at my undergraduate grades, you would have been like, this guy will go figure something better to do than physics. Wasn't actually until I got into research that both the people, like the academics around me and myself, realized that actually this kid might have some talent and a future in this physics thing.
So you almost are you saying you don't have very good grades at undergrad, or just kind of?
Yeah, my grades in undergrad are terrible. By the time I got to my 4th year, I had pulled it back up to top grades, enough to get scholarships for PhDs, that kind of thing. But the challenge I actually had at university was I'm a classic smart kid syndrome. So like I coasted through high school, like nothing was enough of a challenge, especially in New Zealand. We have as much of a like extracurricular push for kids culture. And so if you're a smart kid and you can pass all the tests, there's like not actually a lot more driving you. We're starting to see that changing, especially with the idea, like I think it's becoming more common for Kiwi kids to think about going to, prestigious schools in the Northern Hemisphere, for example, or if you're trying to get to med school, that puts.
So what did you do in all that free time as a kid? What were you kind of up to?
I daydreamed about companies.
Really?
And yeah.
Companies?
So yeah, starting companies. Yep.
Why?
First business I ever wanted to start was a frozen, like a liquid nitrogen flash frozen ice cream store.
Oh, those are great.
So that you could do like customized ice cream on demand.
That's amazing. Those are really
not
good.
just some brand in San Francisco called Smitten Ice Cream.
Yeah.
And then I remember as a kid coming across the fact that Smitten existed. And that was my first like experience of like having an idea, thinking about product market fit, getting really excited about it, and then going, someone else is already doing this. And then needing to convert that into a type of joy that the world is a place that brings these cool ideas into being.
Right.
So I always remember the first time I went to San Francisco and I hunted down a Smitten ice cream and I'm in a park and I'm having this ice cream and I'm like, wow, this is literally the city where my dreams come true. Because I dreamt about this as a kid. And yeah, for me, it was like thinking about different companies I'd start toying, with, back then it was apps were the big rage. Could you build an app and get it on the app store and it could be worth millions or something like that?
So you were an entrepreneur before you were a physicist, really?
It just depends on street cred. I was studying physics. I was reading about Einstein. Another first ever technical text I read that wasn't a textbook was the research final report from Oak Ridge National Labs on liquid fluoride thorium salt reactor project that they ran. And I think I was 13, 14 when I read that. And the reason I love the liquid nitrogen thing was because you were using really hi-fi science to make ice cream. So I don't know what part of that street cred you want to credit first, being the entrepreneur or the physicist.
So Ratu, did you actually start any business as a kid? Did you have any experience with that?
Did I actually end up? I did try to start a LAN gaming center at one point. I couldn't actually figure out, but I got to the point where I was literally trying to get the money and figure out how to finance it and had written the business plan and that kind of thing. That didn't didn't pan out. My proper like business, like small business cred, let's say, is I dropped out of undergrad because my grades were terrible. And with a classmate of mine who was already kind of in the business, we started a paintball field together. So people running around shooting each other. And we put that in Wellington CBD. Like theoretically, you could go on your lunch break and shoot people for fun, as a team building exercise.
Where'd you find the space? The CBD is so small.
CBD is small, and so it was a very particular space. It was an old newspaper printing building. And really interestingly, it was kind of inset from the street fronts. So access was terrible. You couldn't use it for warehousing because the access was terrible. It had no store frontage, so you couldn't use it for retail. But it was big enough to fit, a whole newspaper's worth of printing presses in it. It even still had the old diesel generator inside that they never got rid of. So it was on the small end of paintball fields, but it was enough to,
So this was like an indoor, like multi-story,
yep.
You're running up and down stairs.
There was a crow's nest that you could run up some stairs and get a good view and shoot down at people on, yeah.
Huh.
So I ran that with my business partner for about 2.5 years.
Mm-hmm.
And at that point, I actually figured out how to make myself redundant. It's just like business process development and saying, well, every month I have to do these things, but like I'm very manual about it. And like if I just like simplify and processize a lot of these lists, like do I have a job? And if that's the kind of job I have now, I should just get rid of it. And I probably need to go back to university and finish my physics degree. And for me, that was the answer to the smart kid syndrome problem. Like, if the problem of not being pushed in high school was that I didn't get taught a work ethic through academia. And that's what bit me in the ass when I got to university, was my relationship with academia was so muddled because of that high school experience that I wasn't going to learn a work ethic. Even once university got hard, it was just hard. I was confused and I had none of the tools to deal with it. Whereas a small business, like you have no choice but to work hard. And actually all entrepreneurs almost always drive themselves up to their red line anyway, given the right environment. And so I learned my work ethic. Yeah. Scooping up paintball sludge and getting shot in the crossfire by, my patrons. And that was fantastic because when I went back to uni and they said, and here's your math assignment, spend a couple of, and I just looked at them and I said, you want me to spend a couple of hours just thinking about math problems? Sick. I can do that. Like it was just none of the anxiety and all of the focus, and just got on with finishing my degree and learned a bit more of the academic game, figured out how to get my grades up, all that kind of thing.
Fascinating. Is that business still around?
I think my business partner actually just sold it to someone else. I don't know who he did, but one of our paintball fields is still operating. So at one stage, we actually had 3 paintball fields operating. We actually used that to move away from the original one. So a little bit of business lesson. The problem with an inner city paintball field is you actually pay rent because the land is actually valuable. And what we didn't appreciate about our competitors until we acquired one of them was they were paying no rent. Like they had just found distressed land in some random suburb, either from the council or, some, off the beaten track landlord that couldn't be used for anything else. And so one of our leases was $365 a year. It was literally just $1 a day.
$1 a day.
$1 a day. And what we realized was we could acquire that company because what we had done was we'd basically taken 80% of the demand for, paintball in Wellington and concentrated that into our center city field because it was much more convenient. It's a coordination problem. You need to get all your mates to come together to sign up for a game. And one of them is going to have some logistic problem and then it all falls apart. And so the likelihood that you can actually pull it all together on the logistics of doing it in town and then sell them and going and getting a drink afterwards, hopefully not beforehand, but that certainly also happened. Was just significantly higher. And so we sucked up all the demand, basically starved out our competitors. But we needed that demand to service the lease. And so we weren't actually making any money. And so we actually ended up making much more money once we acquired those businesses.
Wow.
And then downshifted, like we didn't want to be our own competitor. So once you have the cheap paintball fields to run, it doesn't actually make sense to run the Central City one anymore either. And so shifted back out. That business was never going to make more money than what you could justify paying the manager to run it. So it's like the definition of a lifestyle business. But it's fun learning a lot of these lessons, in the hard.
That's the classic like Silicon Valley monopoly playbook, right? Like you come in, you displace all the bookstores, you sell them online. And then you're like, actually, maybe we'll have a couple of physical bookstores. So like,
keep your brand alive.
That's
Cool. Well,
interesting.
let's get back to academia. You decided you went back to university, and then you thought, okay, academia is not so bad after all, and then you decided to go for a PhD in Wellington. What was that in? So what was your kind of specialization that you were going for?
So the first step was to finish my degree. So finish that in physics and economics in undergrad. And then the PhD, the thing that Wellington in particular was world class in, that I found most exciting was superconductivity. And so I remember actually got taught this in undergrad, but like I did an undergrad lab once and it was on superconductivity. And it wasn't just the classic experiments like little magnets levitating on top of frozen superconductor. Lecturer, basically, he had superconducting wire, and he said, this wire here was patented across the bay at a place called Robinson Research Institute. And I was like, holy shit, this isn't just happening somewhere else in the wide world. It's like a 20-minute drive from here. And that planted the seed. And as I started to appreciate more about the research that had been happening there, I became progressively more excited about joining. So I actually got an opportunity to do a summer scholarship before starting my PhD. That was my first proper taste of independent research, which was fantastic. Summer scholars, like you're doing an internship, it's not necessarily meant to be independent research, but if you're capable of it, like your supervisor will leave you alone to do whatever you like if you're actually producing good results.
So did you at that point kind of feel like I want to be a researcher, or I want to like focus on this field? I have this question I want to answer. What was your mindset at the time?
I think it was still very much that I wanted to take insights about the physical world and see how they could change life for people, and particularly that commercialization approach. And so in that respect, why Robinson was so exciting was kind of twofold. One was that they paid a strange amount of attention to that process about how to get these kinds of technologies and products into people's hands. They had multiple collaborations with companies that were making superconducting wire, because that was kind of the stage that the industry was at. And we were just about to break through to the next step of, well, I can buy enough wire to make something useful. And so again, like that, they were developing superconducting transformers for grid applications, like a 1 megawatt transformer. And so there was always this eye on, here's this amazing technology, how do we get it to an application that would make a difference for people? That was one thing. But the second thing was actually superconductivity is just a bit magical. Like if you were looking for something that was as close to magic as possible, literal stuff floats for no perceivable reason.
So wait, how's that different from regular connectivity and regular, I guess when you're talking about floating, you're talking about like magnetic forces, right? Can't regular magnets do that?
So regular magnets can't float stably. So like if you take a maglev train, for example, those use conventional electromagnets, but you need to add computers and feedback control to stabilize the levitation process. Otherwise, they're unstable. Superconductors will levitate intrinsically. They don't need feedback control, they just do it. And so you can do a little benchtop demonstration for people. You can look it up online. There's lots of videos. The classic one is you build a track of magnets, and then you get a piece of cooled down superconductor, you kind of squeeze it onto the magnet, it kind of locks in the magnetic field as seen by that piece of superconductor, and then you send it on its way and it will weave around the track, perfectly levitated. And so there's just this like visceral, okay, if I'm looking for something that seems to be a fundamental hack in the way the universe works compared to all of my other standard perceptions about how reality works, this seems to be one of them. And then the question is, does that hold up under scrutiny? Like, I'm not saying that people should run around just trying to find the most magical thing they can, but does that sense of really orthogonal opportunity continue to persist as you learn more about the science or technology that you're looking at? And in the case of superconductivity, it totally did for me. Like, there are just so many examples of problems or markets that looked really differently or looked really different if you had access to superconductors and the kind of engineering you could do with them.
Can you name a few?
And that was enough to get me hooked. Well, fusion is one. So we're building fusion reactors. You're building really powerful magnets. A lot of fusion research up till now has not been done using superconductors. It's been done using really powerful copper magnets, because what the researchers cared about was getting the magnetic field so that they could do the plasma research and figure out if they could create and sustain fusion reactions in a superheated plasma. But those magnets being copper means that it's a showstopper for efficient electricity production, because the amount of current current you're driving through those copper magnets dissipates an enormous amount of heat. If you actually look at the kind of energy bill for those classic fusion experiments, it's almost all on powering the copper magnet to hold it, to hold the plasma in. And superconductors are the enabling insight that huge chunk of energy that you spent running those magnets can be squished down to almost zero using these superconductors. They come up with all sorts of other pains, but we're pretty confident we can figure those out, whereas just the fundamental dissipation of copper is just a rule we have to play by. So copper's out, superconductors are in. Then there's the research I was doing in hybrid electric aircraft. Using superconducting hybrid electric aircraft.
Hybrid electric aircraft, okay.
Yeah, Skypress. So taking superconductors so that you can get motor generators that are small enough and power dense enough, so about 3 times better than what you can achieve with copper, and then putting that on aircraft so that you can move away from pure jet fuel and actually start to move into hybrid. And then as battery technology catches up, you can then move to full electric. And what I'm talking about is really planes bigger than 20 seats. 20 seats, we seem to be able to do it for small flights with copper, but that does not solve global air travel. You need your jumbo jets to get the number of people around at the distances that we care about in the modern society. And so hybrid electric aircraft, super important. The kind of more abstract realization that I ended up having toward the end of my PhD was that the modern power handling technology that humanity uses today is semiconductors. Now, semiconductors are also very famous for being the basis of all of our computational technology. So all the processors and all the computers and all the server farms, that's all semiconducting switches. But we use those same kinds of materials to create switches that route energy into different places and allow us to manipulate energy. And so our grid, our phone chargers, like every stage from the power plant all the way to your phone charger and then into your laptop, probably has some kind of semiconducting component helping manage what form that energy takes.
Mm-hmm.
And I think one of the bigger insights that I had toward the end of my PhD was that there's a huge opportunity in replacing that semiconductor technology with superconductor technology to handle the power, because the rules are quite different. They're kind of reversed. Semiconductor technology, very good at high voltages, but struggles the more current you try to push. And so we've ended up with a grid that is very voltage heavy. So high voltage lines, the longer distance you're transmitting energy over, the higher voltage you go to in order to do so. Superconductors do the opposite. They don't like voltage very much. So if you want to make a 1 kilovolt a superconducting power handling system, that's going to be potentially problematic, but they handle current extremely well. So you can go to kiloamps and mega amps of current in quite achievable form factors.
So during your PhD, did you already look at nuclear fusion and levitated dipole reactors? When did you come across that, and when did you get really excited about that?
So answer to the first part of the question is yes. It became pretty apparent even before I started my PhD that fusion was going to be the kind of killer app for superconductivity. A couple of reasons for that. Like a lot of those other applications are more price sensitive to make the economics work because there's like a really strong incumbent in the way. So you're either like competing with aluminium or copper, systems that already exist. Whereas fusion, you're taking the advantage that a fusion reaction produces 1 billion times more energy than the equivalent chemical reaction. And so the opportunity is enormous. And it actually means that fusion machines fusion projects don't care anywhere near as much about how much the superconducting wire actually cost at the beginning. In the medium to long run, we do. But we expect those prices to come down as we acquire and produce more of our superconductor. But in the medium term, if you're looking for that first kind of killer app to drive adoption of superconductivity, it was probably going to be fusion because the amount of wire that they needed was enormous. And the economic justification was was even bigger. And so it became like pretty obvious to me even before I started my PhD, that fusion was going to eat my industry. And I could work on hybrid electric aircraft and motors and generators and that kind of thing. But the opportunities were probably going to be delayed 10 to 15 years just because of where the focus was going to end up. I got into superconductivity because I thought the space of possibility was the biggest and most uncharted that I had seen in all of the different technologies or, pieces of physics or science that I had come across. And the fact that, having made that judgment and then turned up, and then like a year or two after they turn up and say, actually, commercial fusion is possible, right? And we're going to build $1 trillion industry off the back of this technology. I was like, oh, that makes sense, I suppose. It, exceeded even my kind of initial expectation on it. And so at that point, I signed up for a PhD working on hybrid electric aircraft. And that had particular importance for New Zealand because honestly, we won't be able to hit our climate commitments and maintain the level of air travel that we've become accustomed to without dramatically reducing the emissions associated with air travel, either through synthetic jet fuels or hybrid electric approaches.
And is it not possible to have a purely electric aircraft? Do you need to always have a hybrid?
Not for long distance and high carriage. So batteries are just too heavy. Now, if you look at the rate of battery improvement, you can definitely just extrapolate the date that you think that would shift and that pure electric would be viable for large scale commercial air travel. And that is absolutely coming. But in that sense, the hybrid transition is the same as we see in vehicles. If you're Toyota, you make it early on that you cannot scale pure electric cars to the level that matches Toyota's ability to make cars fast enough, but you can pull it off with hybrids, right, as a kind of transitionary technology. Now, then I think the mistake that Toyota then makes is that instead of going to electric, they go to hydrogen. But as a transitionary technology, it's the same argument for aircraft, that you want other different parts of the system mature and improve at different rates. And so the superconducting part of the system is ready, ironically, before the battery part. But like an aircraft is the most extreme challenge you could give a battery in technology. Like a car, you need the batteries to be light, but a car still sits on the ground. So it's batteries for aircraft is true hard mode. But if you think those trends and improvement will continue, we will absolutely see pure electric flight in our lifetime. But we can get a lion's share of the improvement before that by moving to hybrid electric.
So back to nuclear fusion. So yeah, you thought this was the killer app for superconducting, and then go from there.
So thought it was the killer app. Still had a PhD to do. Luckily, the PhD was it was motivated through hybrid electric aircraft, but really what we were looking at is the key enabling technology to make it all work. So the key challenge for a superconducting device is that when you build them in the lab, you can put them on a benchtop, you can connect them to a really big heavy power supply, and then you can connect that big heavy power supply to the grid directly. And the question for us for planes was, well, we can't afford the weight of the big heavy power supply to make this magnet work, and we can't connect it to the grid. So you really quickly feel like you end up in the same place as you were before with the heavy batteries. It just doesn't seem to work.
What do you put solar panels on the plane? Does that solve anything?
You can do that for 1 or 2 passengers. Totally.
I see.
Yeah, to put it in perspective, a jet turbine on a commercial passenger aircraft is a multi-megawatt energy device, right? It's another way to put it. This is actually one of my favorite ones. Is if you look at Auckland Airport and you look at all of the jet fuel that gets piped into that airport to fuel up all the planes to then go take off. If you were to electrify that energy, and so instead of jet fuel, you were just charging batteries, that would be the equivalent of 70% of our existing electrical grid in New Zealand piping into one airport. The energy demand that we're talking about is obscene. You could describe that in terms of solar panels. How many solar panels would you need to replicate 70% of New Zealand's grid? And you can just very quickly imagine it would be a lot. And then you look at the area of all the wings on all the planes, and you just see that they just don't match at all. And it's just solar is not a very energy dense source. It requires a lot of surface area. But there are really cool perpetual gliders that just go on and on and on because they're solar. So it's great for getting information, and observing the world, and maybe going for a joyride, but it's not going to solve the move lots of people a long distance to keep society interconnected.
Makes sense.
Back to nuclear fusion.
And okay, so we've got these closed systems in these planes. That's what we're doing in the PhD is we're trying to make superconductors work without the power supplies, without the direct connection to the grid. And the key technology that we had at Robinson Research was these superconducting power supplies. And they could produce a huge amount of current in a really small form factor. They couldn't produce a lot of voltage, but we didn't need the voltage. We wanted the high currents to create these strong magnetic fields. And when you looked at the engineering, you said, well, as long as I keep it cold, I probably only need a little bit of electronics and a small battery pack to keep it all running. And as an overall kind of part of the aircraft, it looks very modest. Like it's almost not even worth worrying about from a kind of weight and power perspective, and allows you to just focus on the motor generator. And so what we call them, they're called flux pumps in academia. I prefer to call them superconducting power supplies. But that technology was key enabling for using superconductors in aircraft. And the big question for me during my PhD was, is this key enabling technology elsewhere? There's a few applications in space and satellites where it's probably also key enabling technology. But the thing and then in fusion, it was very clearly economically advantageous technology. If you think about how you run the really powerful magnets, swapping out the traditional power supplies for these superconducting ones would just save you money. It would reduce the amount of energy you spend to run the power plant, and that energy in sell instead of consuming it yourself. And so it was clearly going to be an economic boon, but those other fusion projects weren't going to prioritize it because it wasn't in the way of success, right? It wasn't standing between them and getting to market and proving that fusion is possible. And so I wasn't going to go to one of these companies and say, hey, hire me to keep working on this cool tech that I did in my PhD. What ended up happening probably halfway through my PhD is a friend of mine came back to New Zealand. He had just done his master's degree in Tokyo, and down the hall from his experiment, which was a tokamak, there was this thing called a levitated dipole, and it was super obscure. There's only been 2 substantial experiments built, and the one at MIT had been shut down, so there's only this one experiment left in Japan that was still operating, and I was extremely lucky to have had a friend who was so proximal to it and then came back to New Zealand, and I had convinced him to come to Robinson to get into superconductivity, to get into fusion. And the crazy thing about it, and I actually still have this experience today, was I had never heard of it. Like the trend that I'd seen in my industry was that fusion was going to eat it. So I had been looking at all the different ways you can do fusion. And there's lasers, big magnets, tokamaks, stellarators, mirrors, cusps. Like it's a zoo of different ways of arranging magnets and plasmas and all sorts of things.
Maybe, Ratu, maybe if we just pause right there, what does it mean to do fusion? What's actually involved in all these different permutations of doing fusion at a very high level?
At a very high level, in a fusion machine, what you're trying to do is replicate the process that happens in the sun, which is under extreme temperature and pressure. You get the nuclei of atoms, usually isotopes of hydrogen, to actually get close enough that electric repulsion gets overcome by nuclear attraction, and you get fusion. And the benefit of this is it produces energy. And so that's why the sun shines, is that it is constantly doing this process, and that is creating the heat that allows it to actually keep going and keep going for billions of years. So it's nature's kind of preferred energy source.
Why does it, so like whenever like 2 things like are touching, like things that are like keeping them like repelling is the electric, like the electrons basically, right? Like when like my 2 fingers right now are not able to touch, like kind of go through each other because of that. But if you sort of just literally squish them close enough together, that what is that called? The some kind of nuclear force or something?
Strong nuclear force.
Strong nuclear force, yeah. So why does it release energy?
It's actually not that different to any other reaction. So be it a chemical reaction, which is manipulating the electrical force, so the way that electrons arrange themselves around atoms and compounds. Like when you burn fuel, you're basically just taking one arrangement, rejigging it into a new arrangement that nature prefers, and you get the energy out for doing that. The nuclear version of that, so fission, is taking big things that are a bit like atoms that are a bit too big, or nuclei that are a bit too big to be happy. And if you could just pull them apart from each other, they would be happier being smaller, and that excess energy you get out. And so that's how a fission power plant works. And fusion is the exact same logic, except it's smaller ones want to come together to make a bigger one, and that's the happier arrangement. And logically, there must be something in the middle that's the perfect size. And it turns out it's iron, which is why iron is so common. And so all processes, be they fusion or fission, eventually try to get you to iron. Now, most processes stop at some point, so you still get all the other elements, but iron is kind of the end of the road. It's the most nuclear stable.
Is that why most asteroids are like mostly iron or something. Is that right?
I could be speaking well outside of my scope, but yeah, basically. It's just very common to be around that range. It's a common in-stop in both directions.
So what is the actual, can you explain the difference between a more traditional reactor like a tokamak and what you are doing? So in very easy terms, I guess, so that we all understand.
So in all of these different ways of doing fusion, there's one that stands as the kind of orthodox approach. It's one that we've spent the most amount of effort on, we've made the most amount of progress, but at the same time, you could describe it as the devil we know. It has proven the best performance in terms of being an integrated fusion device, and it's worth continuing to push it and seeing if we can get it to economic power generation. So this machine is called the tokamak. It's the standard way of doing fusion. And what a tokamak is a set of really powerful magnets, and you arrange them in a donut where the inside of the donut, so the cross section, if you take a cross section of that donut, these are the magnets, and inside that you're producing a very powerful magnetic field, and you're using that magnetic field to hold on to this really hot ionized gas, or plasma as we call it. And if you can hold on to it hard enough and get it hot enough, you will get fusion reactions out of it. Now, the thing that's important to keep in mind is that basically means that you have a plasma inside the set of magnets, because the magnets made that magnetic field inside the set.
And
now,
is the reason you use magnets because you can't hold the plasma using anything else?
Yeah, it's kind of twofold. Everybody thinks about it in terms of, oh, that plasma looks very hot. Surely it would destroy the machine if you accidentally touched the walls. That's certainly a consideration. But actually, more importantly, is you cannot get the plasma hot enough if it touches anything else, because it just cools down too quickly. Like, in order to get it that hot, it has to be levitated and held away from any other physical object. That's how far we've pushed it. And magnetically confined plasmas can get to the temperatures necessary to achieve fusion. But yeah, you're not allowed to touch them.
Ratu, have you ever seen this levitating plasma like with your own eyes?
We've generated plasma at OpenStar, so we achieved first plasma in our prototype back in October. Unfortunately, radiation safety rules stopped me from witnessing the event with my naked eyeballs. So there are still a couple of cameras, a camera and a screen in between me and the event. But I feel very good for being very adjacent to the event and the room separated, and all the pride and joy of having actually built the machine. Unfortunately, at the scale that we're operating at, our devices produce X-rays, which in the grand scheme of radiation is not a big deal. In fact, our device is rated as a same class of machine as a dental X-ray. So actually, I have been exposed to that level of radiation to get a scan of my teeth. But that had a legitimate medical purpose. And the way we treat radiation safety, which is very reasonable, is that you can only expose humans to radiation to the degree that it's useful and reasonable. And me putting my eyeball on the glass so I can see the plasma, unfortunately, is not considered a reasonable excuse to expose me to those X-rays.
I just meant more from the point of view of you've seen it, right? And it's just such a alien concept for most people. I think that there's this like a flow.
There are plasmas in everyday life. So those lightning balls that you see and you can put your hands on them and the filaments rearrange themselves. Those are a type of plasma. But anytime you've pulled a plug out of a socket and you've seen a spark, that's also a type of plasma. And honestly, if you look at the sun, that's a huge ball of plasma. So these things are around, but the kinds of machines that we build to hold on to them and the kinds of plasmas you get, they are very ethereal compared to kind of the everyday experience. The kind of machine that we're building, so talked about the tokamak, you've built this powerful magnet, and inside those magnets you get a plasma. We flip that on its head. So we build one magnet rather than a set. So we have one magnet, and through the middle of that magnet and then extending out into a large space, we produce a magnetic field, and that magnetic field holds onto the plasma. But now that means our magnet is inside of our plasma. And that is the source of all of the engineering challenges and therefore the commercial opportunities to basically protect the concept as we solve those challenges. But also the source of what makes our concept unique is that this is the only way of arranging a plasma that you can achieve in a lab and is found in nature. So there is a plasma that looks that way above our heads right now. We call it the magnetosphere, and it's the Earth's magnetic field holding on to a plasma, and that's mostly particles that have come from the solar wind. But the fact that that plasma exists, it's stable, it's been there for about 4 billion years. Mars doesn't have one, And that's why Mars doesn't have an atmosphere, because our magnetosphere protects us from the solar wind blowing away the traditional atmosphere. So life as we know it already owes its existence to what we would call dipole plasmas, like the magnetosphere. And what we're trying to do at OpenStar is replicate that stability, use that stable plasma configuration as the foundation, and then build that up and scale it up in the same way that we've seen with the other concepts to get a plasma hot enough to fuse, because the plasma above our heads is nowhere near hot enough to fuse, which is definitely a good thing. But we think we can do that in the lab and actually take those additional steps. But because you started off with stability as your base, as you make the machines bigger, they stay simple. And that's traditionally been one of the challenges in fusion, is that as you increase the scale and the energy that you're trying to manage, you're constantly trying to tame different types of instabilities that occur in the plasma. And we think the best way to avoid that is to start with something that was stable in the first place and just work within the challenges that that gives you initially.
I see. Right. So the magnet, what shape is it also a donut, or what is it?
It turns out to be a donut as well. But this time, it doesn't produce field inside the donut. It produces field through a major, kind of the big hole in the donut.
So like sort of like around it.
Yeah, exactly.
Interesting.
What is the milestone you have achieved in October then? Why is that such a big deal?
So what we've been trying to do is build these devices, and they were pretty obscure. Like when I was first told about levitated dipoles, I had never heard of them before. There's only one operating in the world, and it turns out it's because they're quite hard to build. And the engineering frankly looks pretty impossible to most magnet engineers, and that had stalled progress on the concept. And that kind of initial technology that I was talking about for aircraft, these superconducting power supplies, it turns out that it's not key enabling technology for other fusion concepts. It might be economically useful, but it's absolutely key enabling technology for the levitated dipole. And so it answers the question, how do you get a superconducting magnet that can levitate inside the large chamber, be completely disconnected from the external support systems, just like a plane would be disconnected from the grid, and be able to operate that magnet long enough to be useful? And so the milestone that we hit back in October was building that magnet. So a modern superconducting magnet with one of these power supplies on board being used to energize the magnet, and then integrating a full system around that, vacuum chamber, heating systems, docking systems, everything necessary to make it all run, and then pulling that magnet into the middle of the device and striking first plasma. And you're going to make me blush.
So what are we watching here? Can you explain this?
So what you're watching, so in the middle of the screen, that's the magnet itself. You're seeing it from the side. So if you were looking at it from above, you'd see the hole going through the middle.
Uh-huh.
And what you're seeing bloom out around it is the plasma. So as we're pumping microwaves into that chamber, we're ionizing the gas that's there. Once that gas is ionized, it hangs on to the magnetic field being produced by that magnet and fills out that whole chamber. One of the things that's actually hard to get an appreciation for in this video is just how big this system is. Like, I could tell you that was sitting on a bench top, but actually that vacuum chamber is 5 meters across. It's one of the largest plasmas it's actually just a huge plasma. In the grand scheme of plasmas, it's actually enormous, with a relatively modest magnet on the inside. As we increase the power, the way that plasma looks will change. You can put different gases in, different amounts of heating power, different strengths of magnet, and kind of all changes these things. People often think that what we were going for was like a science milestone, like how hot did we get the plasma? That's not entirely the focus. What we were really going for was an integration milestone. So having the new superconducting power supply technology, the modern magnet technology, and the heating system in the plasma, and showing that they all worked in some form, integrated all at once. It's kind of a definition of how you improve the technology readiness level of those things. So that was a demonstration that you can get it all to work at the same time and you haven't missed anything, right? Like, you can imagine plugging two things together, but until you actually do it, you have not fully considered or appreciated the different interfaces that are involved and the different requirements that might exist. And so forcing ourselves to go through that project and actually delivering that machine shows that these technologies can work together, and then validates the pathway that we're proposing to get to a dipole fusion reactor, which is really hinges around the notion that these magnets can be built at really high performance and at sufficient scale and with sufficient uptime, so time before you have to reconnect them, to actually make a useful power plant. So that was the first step demonstrated in the flesh.
Were you anticipating that you'd see plasma?
Yeah, absolutely. So one of the members of our team, Dr. Darren Garnier, he's our director of plasma science, and we pulled him out of MIT. He was actually the chief experimentalist on the device that they ran back between 2004 and 2011. He's been waiting for like a decade to see dipoles come back to life. So we called him up one day once we were ready to kind of reveal that we had been working on this, and said, hey, look, do you want to come join and help give a rebirth to this technology? So the machine that we built is actually of the same scale and performance target as the machine that they built at MIT, but the key difference being swapping out the magnet technology. And so that magnet that they built at MIT, it wasn't going to scale to power plants, but with this new magnet technology, we see a full pathway. And so we were basically saying, well, we at least need to be where academia was at as a baseline, and then we need to de-risk the key enabling technology that we think unlocks that pathway.
How fast did it take them to build that and get to that same demonstration, and how long did it take you?
So it looks pretty different. The MIT team started in around the mid-90s, and they turned on the device in 2004. And so there's a lot of talking about it beforehand and getting a little bit of money and starting a little bit of work. And, it's an academic project. The team is relatively small. You've got a lot of students coming in, contributing different parts. But you get to 2004 and then you operate it for 7 years till 11. For us, we...
About 10 years for them, right?
Yeah, to get to that first plasma for themselves. Now, that matches the environment that they were in. They were getting public funding, and public funding is often not so concerned with pushing the timeframes as it is at being deliberate at taking kind of each next step. OpenStar is a venture-backed startup, and one of the things our investors care about is retiring risk quickly in order to get a return in a reasonable time frame. Like, I can tell people that I'll 10x their money, but if it takes me 100 years, who cares? Stock market definitely would have achieved that. And so we said, we need to achieve that milestone. We think we have a technology to do it. And so we pulled that off, and from receiving seed funding and to pulling it off took us 2 years, and we had spent about $10 million equivalent to do so. So one of the fastest kind of fusion startup projects in the world, and certainly the cheapest to get to the milestone that we did. And a lot of that is to do with kind of a scrappy Kiwi way of building companies and being laser focused on the mission. And then some of it is also the concept itself really lends itself to like rapid development. And then you build a company that kind of creates a positive feedback loop between those two things. So for example, in that 2 years, it took us about a year to design, procure, build, assemble everything for the first time. Tried to go for a plasma, something broke, and we had to pull it all apart again, figure out what went wrong, figure out how to fix it, put it back together again, and go for another shot. Those iterations took us, on average, about 2 months per iteration. And so by the time we got to that first plasma, we had actually iterated that machine probably 6 times. Now, not everything changed each time, but there are components that make that all possible that are on their 4th version in order to actually get there. And that kind of iteration and learning through doing is really hard to pull off in other fusion machines where things are bigger and more integrated and just more of a challenge to pull apart. And so it's that iteration rate. Another good way of thinking about it is if that dipole took us 2 years to deliver, the equivalent kind of tokamak project is more like a 10-year project. And so looking at a really different scale on how quickly you can iterate and learn on these different technologies.
So does that mean that you're trying to get to, or that you're thinking that you can get to commercialization faster than with with the other method? And what kind of time frame are you thinking about?
So in our internal thinking, we usually scale each step of the dipole as being a 2 to 3 year project. And so if you look at that, we've just delivered our first machine. The 4th machine we deliver like the fourth scale of machine we deliver, that's the one that's going to be a power plant. And the intermediate two are the ones that are slated to kind of de-risk the other things that you need to in order to get to that power plant. And so if each, we've done the first one, so that means there are 3 more. And so you're looking at 6 to 9 years in order to get there. And like, it has to be, right? If this is getting to the first power plant, not the 1000th, we have a climate crisis to solve and we need to get to 0 emissions by 2050. So we really don't have that much time. And once we turn that first fusion power plant on, we need to build a lot of them very quickly. And so these timelines need to be aggressive, and we need to be working on technologies that are actually capable of keeping up with that pace. Now, some of the other technologies have been worked on deeper, with more capital for longer, so they have a head start, is their answer to that question. And so given that we don't have the head start of some of those other concepts, the thing that makes the dipole viable at all is the fact that it can be iterated. If the dipoles took 10 years apiece, I wouldn't be running this company. We're just built tokamaks. But at that faster iteration rate, we have a chance to get to commercial application faster. And once we're there, we have a chance to dramatically improve the pace at which we learn, the pace at which we improve the economics of those machines, the way that we cost learn that process by just producing more units and figuring out how to scale that production. All of that is easier in a modular type system like the dipole.
There's some kind of a story about the Wright brothers and the reason why they figured out flight and this other guy who's funded by Harvard and everyone else was basically because they were just iterating once a week or something. They would just optimize for iteration time versus optimizing for just solve the problem, which I found a really interesting way to think about
it. If you have a textbook that describes how to build the thing you want to build and you're happy building it that way, read the textbook. Be deliberate. Take time in the planning phase and try to build something that works first go.
Mm-hmm.
No one's ever really built the thing you're trying to do before. And you can't find the been there, done that type. You can't find the textbook, but you think you have a good pathway for it. Iteration is king because the doing teaches you what that next step needs to be. And you, by the end of it, by the 6th iteration, you will be able to write the textbook. And the next person to come along, they won't need 6 iterations. But as long as those iterations are not too expensive and can be done in a timely fashion, it's a perfectly reasonable way of pushing forward and doing things no one's done before.
Ratu, so say you solve or you figure out how to do this. What's the goal? What's the goal of the company? What are you trying to do? Are you trying to create fusion as a product that you then sell as a utility? You're trying to create these reactors you can license to people to make. What's your vision for how you bring this to market?
I mean, energy is a complicated business, and it has some really big players in it, and it has lots of different moving parts depending on what different type of energy technology that you're looking at. And fusion will share some similarities in the way these businesses are structured to other technologies, but it will also have its own unique attributes just to do with how the technology comes together and what's kind of optimal in structuring that business. The dream is to make energy so cheap that you wouldn't even need to meter it. The kind of big way to think about this is we all grew up and introduced broadband internet, high-speed internet, moving away from dial-up. But when we got that high-speed internet, we didn't pay for it the way we do now. We paid for it per gigabyte, and you would run out of gigabytes and you had to buy another package. And that's how we sell energy today. You have a connection that could bucket unlimited energy into your house at the bandwidth of that wire coming into your home. But you don't do it because you have to pay for every bit of energy that comes in the door. Fusion is a pathway to making energy so cheap that you don't bother tracking who's using what and why. But a household will still have a modest connection to the grid compared to a factory. And the way that you work out all the pricing and economics is that, if you want to build a factory and you need to consume a lot of power, you're going to pay for a bigger connection. But the specifics of how much you use and when and why melt away as a rounding error compared to just assembling the whole system. So that's the highest level dream of what fusion actually unlocks, as just a step change in how energy is thought about in our lives.
Interesting. Why is that true though? Why does it become so cheap? You don't need a meter.
Well, if you look at, say, coal, there's always going to be a fundamental component of burning fossil fuels that is dependent on the fuel input. Right, you had to take some fuel and you had to light it on fire and then sell that energy to somebody. And digging that fuel out of the ground cost money, and the capital of the power plant also cost money. But fusion eliminates the fuel part of that equation. In the long run, it will also reduce the capital part of that equation as well. But if fusion, let's just say that fusion is a pure capital investment for energy, it doesn't have an ongoing fuel component, that's actually the same way that the grid works. The grid, your transmission connection, is a pure capital investment in connectivity. And so just like a broadband operator has a network, and they're load balancing all the different people's demands at any given time, they may decide to throttle speed from time to time, right? You may not have a fancy connection that guarantees you fast speed all the time, but
Henrik definitely doesn't have that.
No, it doesn't.
No, clearly not.
But you don't worry about the particulars of how much people used anymore, because you already spent the money on the capital in order to have the bandwidth in the first place. And so fusion has that element in the long run. In order to achieve that, you've made fusion cheaper than everything else, though. Like that's the bar where that starts to transition.
What's the time frame you think? So you're saying like roughly 10 years for you to create the first kind of power plant that you can commercialize. What do you think is the time frame for energy abundance, that we all access energy at, almost no costs? Is that, 15-year, 20-year project?
True energy abundance, that is like the end of my career. Yeah, like that's my whole life's work, like tackled. And the reasoning for that is that we've got a couple of stages. A, we need to make fusion work. B, we need to start deploying it at scale. There's actually a particular moment where all the new energy generation is now fusion instead of other things, right? So that's a critical turning point. But even that's not enough, because that's just like the growth. That's like if you take current energy usage grows 3% per annum. So every year we add another 3% capacity. When's that all fusion? That's the first milestone. And even once you're there, you've just gotten to the point where you're keeping up with the growth of demand for energy. And then you need to go beyond that and start chewing into the existing energy base that's fossil fuel based. And even that's not enough to get to like the truest version of energy abundance, in the sense that 3% per annum growth, you want that to keep going as long as it contributes to improving people's lives. And so we will replace the fossil fuel base of the energy grid, in some time frame, hopefully around 2050, but we will keep going. Right? Like there is more benefit for humanity after that point. And one of the things I like about energy abundance is that I'm actually not creative enough to figure out what we'll do with it. Like I think it creates a generation of entrepreneurs and people and cultures and a new version of society that can have much more imagination than just me, sitting with my view behind me, pondering it. The kinds of things that we're going to do are going to be amazing. And so that's my whole career. That's totally fine. Maybe my kid's career too. That would be lives well spent.
Do you see a parallel of that with the AI stuff happening now, where the cost of like intelligence is basically kind of trending down to zero, and people can now, coding is becoming really, really easy. You can build stuff that take you many developers, many weeks or months. You can build stuff in hours. You can write stuff, right? You can create images, create stories. Image generation is now so good. You can create movies. Like you can now and you're seeing people create all kinds of stuff, and companies getting to like 5, 10, even 20 mil ARR within a year. Kind of, do you see a parallel there with what we'd see with energy? And what do you think of the AI stuff?
I mean, AI is really interesting for us because it's extremely energy hungry, right? Like, what are we doing with this energy growth? What's driving it? A good amount of it is data centers, and it used to be for cloud, and people thought cloud would plateau. And just as cloud was starting to plateau, AI turned up, and we kept building these things. And actually, my instinct is that I wouldn't expect that to stop. Right? Humans are very good at figuring out creative ways of doing cool stuff with the capability that you give them. And AI is the latest version of that in the digital space, in managing information. You could think of like humanity as rearranging energy, material, information, and then consumption. Like our own enjoyment of rearranging those things. And the last, like not just now with AI, but honestly, since the 70s, progress in humanity has been dominated by new ways of manipulating information more efficiently. And we're extracting a huge amount of gain from that, and it has contributed to a measurable increase in the standard of living and like global access to information, right? Like the global internet being able to get anything that you want. And that's going to, again, turn into global access to intelligence, being able to get synthesized wisdom, even if you are born, in the absolute third world. Now, the interesting thing about all of that is the world really is those three constraints. And so it's not just, if I had all the information in the world, what could I do? It's, do I have the resources to be materially wealthy? Like, can I build the houses that people need? Can I keep myself, and then going to energy, can I keep myself warm? And so the challenge, I think, is we're shifting into a regime where that access to information and intelligence and through AI is a driver for rearranging wealth. So for individuals, it's a fantastic way of creating opportunities for them. And hopefully it allows them to rearrange matter and energy in more effective and efficient ways that bring more utility. But what climate change is telling us is that we have unreconcilable problem with energy and material. They're actually fed back. And so if you look at renewables, one of the big restrictions is we don't have enough metal to make enough wire to connect all of it, for example. And then fusion is like really focused on the energy portion of that. Can we make energy abundant? And so the kind of tripartite question is, in a world of information abundance, energy abundance, and material abundance, let's say material abundance is going and mining asteroids, for example, like what could civilization be? And honestly, like the full-fledged sci-fi future of building like intergalactic society, I don't see why it's not on the cards if you can unlock those three things. And we live in a really interesting part of history where we're really overbalanced on, and we have an opportunity to rebalance into the other three.
And is that intelligence?
Yeah, so we're overbalanced on intelligence. We've made huge progress, and we need to figure out how to get that equivalent progress in energy and materials.
And Ratu, I mean, there's been, I think fusion is one of these kind of things that people always say it's like 10 years away, right? People always kind of joke about, like, it's like the thing that you kind of say, like, if it's symbolic, you just call it, it's like achieving nuclear fusion. It's almost synonymous with doing something impossible, right? I guess I'm curious. Obviously, you were exposed to all that. How did you think of, and like, do you think you guys have solved it? Do you think, like, what do you think you guys have kind of done or figured out, both on a science level, but also on like a kind of a psychological level, to sort of will yourself into like believing that you can solve this impossible thing and then actually solving it?
There's a couple of things to that. The first thing is the joke, 10 years away and always will be. The great thing about it is the number changes every year. And so when I got into this, it was 30 years away and always will be. So actually it's like, it will asymptote to its here, right? It's 0 away. It's 0 years away and always was. That's not how I come to terms with it though. Myself, I always, already talked about looking for the biggest opportunities and the kind of green fields of what's possible, but at the same time, getting into the specifics of why things are possible or impossible. Like not just looking at it with surface analysis, but actually taking it seriously and going to the next step. And if I found a good answer as to why fusion wasn't going to happen, right, I'd take that seriously. But the interesting thing about that phenomena, 30 years away and always will be, is probably tainted by this big project called ITER. It's for international collaboration to build the world's biggest tokamak, and that tokamak will produce more energy than it takes to run, but it won't produce electricity. So it's like not even a power plant yet. But that project was so big and so complicated that it couldn't be supported by any one country. So a whole bunch of countries had to come together to make it happen, to actually capitalize it. They can't even agree on how much it costs. The EU thinks it costs 20. The Americans think it's more like 50 billion US dollars, euros, pick your currency. And really, you look at it and you say, well, what was the goal of that project? And people think it was fusion, but actually it had a very important other goal, which was an excuse for the Soviet Union and later Russia and the West to work on something together that was high-tech, good for humanity, but had very little risk on providing kind of weapons technology or military advantage to the other. It was an olive branch for peace. And really that project was a way of bringing the world's countries together in an act of cooperation. And in that regard, it was very successful. If you look at it, a project from a science project and a societal project, it has two goals. And those two goals don't necessarily agree with each other. So, for example, they'll take a component like a we call it a toroidal field coil, like one section of those magnets they have to build. And instead of just building them all in one country and having a factory that gets to learn how to do it really well, so by the time they build the 18th coil, they've really got it down packed. Maybe they have to build a couple of extra. Instead, they split it over, I think, at least 3 or 4 countries who all had to learn it on their own. And it's those kinds of trade-offs that ended up in this like 30 years away and always would be, because you're cross-contaminating it with the most aggressive version of human bureaucracy we've ever invented. And so if you look at it from that point of view, you don't have to like poo-poo it as a project overall. It really did achieve 2 of its primary goals. It advanced fusion understanding immensely as a cooperative tool, and it was an amazing tool in international diplomacy and cooperation. But it ended up giving us this weird perception that fusion just intrinsically has to take a huge amount of time. But that's not true. Like, that's not intrinsic to fusion.
It was a big psyop.
It was, yeah.
Wow.
Based on the milestone that you achieved in October, how much money do you think you need to raise until you get to that stage 4 that you were describing, this power plant milestone?
So I don't know, so a couple of things. We're currently raising that Series A as we speak. And I don't know why you think that's a bad note to end on. At the end of the day, sure, my answer is we probably need to raise $1 billion.
How much?
$1 billion to actually have delivered that final machine and the machines that came before it, and actually build a business that can then take that next step to rolling out power plants. That's probably $1 billion pathway. But building $1 trillion business for $1 billion of invested equity, that's a bloody steal. And so I think that's a great place to end on, right? Fusion is an enormous opportunity.
Yeah.
And in a world where investors are trying to figure out where to deploy capital to generate actual return, fusion is a truly positive sum game, right? We build machines that make energy from nothing, just like you dig an oil well and black gold comes out of the ground for luck and providence of being able to have a permission to dig the hole there. Fusion is an amazing opportunity. And one of the ones I like daydreaming about on capital returns is for my whole professional career, we've lived in a low interest rate environment, right? And be it quantitative easing or what have you, other than this blip with some inflation because of COVID, real interest rates have been preposterously low for our working lives. And I think in VC, there's this idea that they get addicted to it, and it's it forces money into venture and this kind of thing. But the sad reality of it is real interest rates are a reflection of the market's expectations that the world will be better next year versus this year. And what we've been stuck in is this loop that we just don't think the world is actually getting any better year by year. And because we don't have the technology or the industrial base to make it better for our kids. And that's actually what fusion is. It's not just $1 trillion opportunity as, for $1 billion worth of investment. It's actually a fundamental step change in what's possible in our economy that could actually take us back to reasonable interest rates as a reflection of the world getting better year by year.
Explain that. So what you're saying, low interest rates means we think that the world's not going to get better. Why?
The market is just, a financial market is just people who need money later, putting money away today, and abstracting that through some assets, right? And the balance of supply and demand of that is really driven by money is expensive in the future because the future is actually better. Right? So if I give up money today, I need more money back tomorrow, in part because I expect the world to be better and there to be more stuff, right? And so that reality, that being true, settles the real interest rate. All the argument about policy, all the argument about, nominal interest rates, being high as they are now, doesn't mean the real interest rate is high, right? We've been taming inflation under control. Real interest rates cannot not in the long run, a function of government policy. Governments can ruin economies by making bad choices, but it's actually the real action of building businesses, capturing and transforming resource, and actually trying to make people's lives better that actually allows you to move to a high, and then gets reflected in a higher interest rate environment. So that's the way I've viewed my professional life and the economics of it, is that low interest rates are just a reflection of pessimism. And one day we will rebirth and rebuild an economy that's sufficiently effective to make the world a sufficiently better place that if you were to trade money in a financial market, the real interest rate would actually be high.
What's like building a company from New Zealand? And do you imagine being based in New Zealand?
So OpenStar is solving a global problem, and that means that we will need global scale in order to actually get that problem solved. New Zealand had 2 or 3 really unique aspects to it. One was the magnet technology to make our approach possible at all. There was no other place on Earth where the levitated dipole was going to get reborn. I've played out the historical scenarios. I've met all the people in the space now, and to my mild horror, it was actually only going to be here that we were going to be born. And that is actually a lot to do with New Zealand and how our governments over successive decades have decided to invest into different parts of technology and double down into particular strengths. And it turns out that one of them was superconductivity and producing these really advanced magnets. And now that's paying off in maybe the biggest way imaginable. The second thing is culture and people. New Zealanders, as it turns out, really dogged and tenacious and just really focused. But one of the ways I'd put it is I've been able to build a team. We're sitting at about 50 people now, and you tell them, hey, today we're going to wake up and we're going to work on a fusion reactor, and they don't know any better but to give it a shot. And that's not true in other places in the world. Like, different cultures can be significantly more pessimistic or like coax things in wisdom that things are hard or that's going to take, 10 years, 20 years longer than you expect. New Zealanders don't know any better. They will just get up and give it a shot. And that's why we were first to get to the top of Mount Everest. And it's why we managed to stand up a aerospace economy in the matter of a decade. Venture-backed startup style instead of, massive government procurement style. And then the third thing, which is kind of related to that analogy with aerospace, is that New Zealand is a green field for this kind of thing. One of the things with fusion is this big question of, is it a nuclear technology? And in the common parlance, nuclear actually means fission. And so if you talk to a physicist, fusion is a nuclear process. But fundamentally, the way those technologies work and what you need to worry about in each one to make sure it's safe are fundamentally different. And in the rest of the world, that's a regulatory unpicking process that you have to do because everybody else did fission reactors. And so there's this big cloud that's been hanging over all of it. In New Zealand, we never did fission. And so as we move forward with fusion, we can take it from a green field and do it right in a way that actually makes sense. And that's also been one of the reasons why OpenStar's been able to move as quickly as we have on our current prototype. So those are the advantages of building in New Zealand as I see it. And those have analogies across different industries. Those stories play out time and time again for people who want to build hard tech companies in this country. This is a great place to do it. But at the same time, you also, at some point, if you're tackling global scale problems, you will have to get to global scale solutions. And so we're expanding into the US. We have a magnet talent here, but there's a lot of kind of broader fusion talent and plasma talent, as we call it, that we think the US is the best place to go to. And so we're bringing that together as one company in the coming years.
Awesome.
Thank you.
Thank you so much for joining us today. This was
Awesome.
really, really great. Thanks so much.
Thank you for tuning in to TechMates. If you enjoyed this episode, be sure to subscribe, leave a review, and share it with friends. We'll be back soon with more stories of Kiwi and Aussie founders reshaping the future and disrupting down under. Until next time, keep dreaming big and daring to disrupt.